Hi, my name is Or Sattath. I'm a computer scientist at Ben-Gurion University, and I primarily study quantum cryptography. I'd like to start by thanking the organizers for inviting me to give this online talk. This talk is about quantum mining, a topic that has received surprisingly little attention from the research community. Quantum computers have an advantage in mining over classical computers. And if you believe that the transition to quantum mining is similar to past shifts in Bitcoin mining methods, say from CPUs to GPUs, then to FPGAs, and eventually to ASICs, you're not alone. In this talk, we'll see why this widespread belief is a myth. We'll explore how quantum mining algorithms are fundamentally different from anything we've seen before, and we'll discuss the new dynamics likely to emerge between miners, examine the challenges, vulnerabilities, and possible attacks that could arise, and present several strategies for addressing those issues. Throughout the talk, I'll assume that you understand how Bitcoin works. I won't assume any background in quantum computing. Unfortunately, I also won't have time to explain how quantum computers work and the quantum algorithms that are relevant for this talk, though I will provide resources for those interested in diving deeper. The outline of this talk is as follows. First, we'll discuss Grover's algorithm. This is a famous quantum algorithm which is useful for finding a needle in a haystack. And it does so quadratically faster than classical brute force search. This algorithm is the basis for quantum mining and provides a quadratic advantage over classical miners. This is the only quantum algorithm which is relevant for this talk, and I will only describe its properties, not the quantum algorithm itself. In the second part of the talk, I'll describe the setting in which all miners are quantum. The most interesting and surprising aspect of this scenario is that if the current type-breaking rule does not change, there will be a high stale rate. In other words, there will be many more forks in the blockchain. We'll see how this problem can be addressed by modifying Bitcoin's tie-breaking rule. In the final part of the talk, we'll discuss a setting in which there's a single small quantum miner, a miner with, say, 1% of the hashing power, and we'll see how such a small quantum miner can gain full control of the blockchain and perform 51% attacks. We'll also discuss why this attack in its current form isn't practical. So as promised, we'll start with Grover's algorithm. Consider the following scenario. You're standing in front of n closed curtains, in this example n equals 4, and I promise that behind one of the curtains there's a prize. You can ask me to open a curtain, such as curtain number 3, and indeed I'll open it. Unfortunately, the prize isn't there, so we continue. Suppose you ask me to open curtain number 4, it's not there again, and then your next guess is curtain number 2, and this time you're lucky, and you get the prize. Classically, the best strategy to find the prize with as few attempts possible is brute force, right? You just try one after the other. In other words, it can be shown that order n attempts are needed to find the prize with constant probability. Bitcoin mining is an instance of the problem discussed in the previous slide, which is also known as the problem of finding a needle in a haystack. The nonce picked by the miner are the curtain numbers. So specifically note that n, which is the number of curtains or nonces, is huge. A valid nonce is the curtain number of the prize. Note that there are some slight differences. Specifically, in Bitcoin, there are many valid nonces, and we'll address the setting of multiple prizes when we'll discuss Grover's algorithm. Additionally, in the scenario in the previous slide, I told you that you can choose a number and I will open the curtain. Of course, in Bitcoin mining, everything is done by the miner. To open a curtain, the miner computes the hash and checks whether it's below the target. Lastly, the difficulty is proportional to n over k, where n is the number of possible nonces and k is the number of valid nonces. Grover's algorithm is a quantum algorithm that finds the price using only about square root of n steps. So suppose n equals 1,000,000, you can find the price using roughly 1,000 quantum steps, whatever this quantum step is, instead of the 1,000,000 steps required in the classical setting. We'll discuss several of the properties of Grover's algorithm that are essential for this talk. First, the algorithm is sequential and consists of steps called Grover iterations. Crucially, you can stop and measure the result at any point you choose. If you perform q iterations, the success probability is roughly q squared over n. Note that if q is roughly square root of n, the probability is roughly 1. Lastly, if you stop and fail to find a solution, you have to start from scratch. To emphasize the previous slide, these two graphs show the success probability after a certain number of iterations, where n is huge. As can be seen, the probability grows linearly in the classical case in the top graph, whereas it grows quadratically in the quantum setting when you use Grover's algorithm. Now, what this means is that the more time you give a quantum computer to run Grover's algorithm, the greater its advantage becomes over classical algorithms. What happens if there are many prizes or many needles in our haystack? It turns out that Grover's algorithm still works, and furthermore with fewer steps. If there are k prizes, whenever you had an expression with n, it should be replaced with n over k. Specifically, the running time is square root of n over k instead of square root of n, right? And similarly, the success probability, if you run q Grover iterations, is k over n times q squared instead of 1 over n times q squared. One of the advantages of brute force search is that it doesn't suffer any loss when using a parallelized strategy. Here you can use your intuitions about classical miners, right? If you have T classical computers or miners, you can easily divide the mining between these T miners, and the expected time it will take you to find a block will drop by a factor of 1 over T. Unfortunately, it doesn't work the same way in the quantum setting. If it takes a single machine square root of n steps to find the block in the quantum setting, T quantum computers can find the block or the prize using square root of n over T. Note that we didn't divide the expression by T, but rather by square root of T, which is much smaller. Okay. To conclude, classically, T miners are as good as one miner which is T times faster. Quantumly, however, for Grover's search, T squared computers or miners are as good as one quantum miner which is T times faster. Note the difference. To gain a speed up by a factor of T, you need T squared quantum computers, right? which is very different from the classical setting or classical mining. And therefore, I would say that quantum computers do not behave so nicely when it comes to parallelizing Grover's algorithm. As I mentioned, I won't explain the model of quantum computing or the details of Grover's algorithm. Fortunately, Grover's algorithm is one of the simplest quantum algorithms and is covered in virtually every quantum computing textbook. If you want the gist of it, I recommend 3 Blue, 1 Brown excellent YouTube video, which you could easily find in Google, which covers everything you need to know in just 35 minutes. Okay, so now we have all the ingredients to move to part 2, where we discuss the setting where all mining is done by quantum miners. The main points of this part are the following. If the Bitcoin protocol remains unchanged and all the miners switch to quantum mining, the stale rate or the rate of the forks will increase significantly. In the classical setting, a high stale rate is known to have several negative implications for Bitcoin. So we know that it's bad. In particular, double spending attack require less computational power. Selfish mining becomes profitable with a smaller hash rate, and confirmation times increase. We propose a countermeasure by modifying the Bitcoin protocol and specifically the tie-breaking rule, which will be explained on the next slide. So this is a reminder regarding Bitcoin's tie-breaking rule. Suppose that a fork naturally occurs. That is, 2 miners find 2 different blocks, both of them with the same power and roughly at the same time. In terms of proof of work, we have a tie. So miners have to decide which tip will an honest miner try to extend. The current tie-breaking rule is that an honest miner mines on top of the block that it received first. So what are the implications of quantum mining when all miners use Grover's algorithm? Suppose you hear about a block mined by a fellow miner. You now face a choice between 2 strategies. The peaceful strategy is to stop Grover's algorithm, throw away the state, and start from scratch mining on top of the new block. In the aggressive strategy, you immediately measure the quantum state, hoping to find a valid block, right? And try to propagate it faster than your competitor. If your block becomes part of the longest chain, of course, you win the block rewards. Now, which strategy is better, right? I argue that rational miners will use the aggressive strategy, as it is strictly better, right? In the peaceful strategy, you essentially throw away something that might contain the block rewards. Therefore, once one miner finds a block, all other quantum miners will use the aggressive strategy, that is, immediately measure their state in response. This behavior may lead to more frequent forks in the blockchain, as we will discuss in the next slide. Now, this is very different than the classical setting for the following reason. Classically, forks happen due to propagation time or network effect delays, right? It takes a few seconds for a block to propagate to the network, and during that time, forks could arise. Put it differently, the stale rate approaches 0 for faster networks, that is, as the propagation time approaches 0. In the quantum setting, however, forks arise for an entirely different reason, and the stale rate remains non-zero even as propagation time decreases. Here we show what happens to the stale rate in a simple symmetric setting. Specifically, we assume that there are many quantum miners, that is, the number of miners goes to infinity, and that they all use the same quantum hardware, and that all of them use the strategy in which they mine for t minutes and measure according to the aggressive strategy. The graph shows the stale rate as a function of t. As can be seen, the stale rate can be quite high. For example, if they mine for 4 minutes, the stale rate will be about 20%. I won't get into the mathematical derivation of this graph. The closed form formula for it appears in the paper. This is quite technical. And furthermore, unfortunately, we didn't do the game theoretic analysis to calculate the stale rate for the Nash equilibria strategies. So I can't tell you what the miners will actually use as their value for t. But it seems that no matter what the equilibrium is, there will be lots of forks. This is essentially because the graph grows linearly starting from 0, right? Already here it has a non-zero slope. So how can we resolve the issue of a high stale rate? We propose a countermeasure, which is a bit tricky, so I'll do this slowly. We want to encourage miners to use the peaceful strategy, or in other words, we want to make sure that the aggressive strategy won't win block rewards. The main idea is to force miners to commit in advance to the number of Grover iterations they will apply in order to find the block. The honest miner, the original miner, knows exactly how many iterations they would like to apply, whereas for aggressive miners, this came as a surprise, right? They've heard of a block and decided to measure. And therefore, their commitment, the ones that used an aggressive strategy, will in some sense be incorrect. So we will be able to tell that a block which was mined honestly from a block which was mined by an aggressive miner by noticing that the aggressive block has an incorrect commitment. We then use that commitment in the modified tie-breaking rule. Now, recall that under the original rule, an honest miner follows the tip of the chain corresponding to the block that they received first. Formally, let T1 and T2 be the times at which the competing blocks were received. The honest strategy is simply to mine on top of the block that minimizes Ti. Again, that's the current tie-breaking rule. The new rule also takes the timestamp included in each block into account. Recall that every block that is mined, even currently, contains a timestamp. But the timestamp isn't taken into account in the current tie-breaking rule. And will be taken into account in the new tie-breaking rule. So let S1 and S2 be the timestamp recorded in the two competing blocks. The honest miner should now mine on top of the tip that minimizes the following expression. So Si minus Ti in absolute value plus Ti. Okay? Why does that make sense? Honest miners know in advance how many iterations they will perform. So they can ensure that Si minus Ti, this part, is essentially 0. On the other hand, an aggressive miner doesn't know when a competing block will arrive. So if they choose to measure after seeing one, there will be a significant difference between Si and Ti. And they will, since there's a mismatch, right, between the time that they originally intended to mine and when they actually received the block. This results in a penalty, right, in the form of making this expression larger, making their block much less likely to be chosen. So that's it. That's the new tie-breaking rule. So to conclude, the Bitcoin tie-breaking rule must be revised to prevent a high stale rate when all miners are quantum. Some open questions and issues that still remain. So what are the equilibrium strategies for quantum mining? Namely, how long should a quantum miner run Grover's algorithm? This isn't a trivial question because recall that if you mine for twice the time, your chances of success increase by a factor of 4. So clearly you have an incentive to mine for longer times. On the other hand, if another black is found before you finish, you'll have to discard all the hard work from the last couple of minutes. It turns out this is an incredibly hard question, and the partial answer was given by Troy Lee et al. In a simplified setting. More specifically, they analyze a single-shot mining game rather than the realistic setting, which is a repeated game. In the real setting, if you run Grover's algorithm and failed, and no one else has found a block, you can try again. But in their setting, the game is over, and you have to start from scratch, meaning you'll have to wait for the next block. I want to emphasize that this is a very nice and important paper. It presents beautiful game theoretic ideas and techniques, but even so, this paper is already quite long, and analyzing the realistic repeated game setting remains an open problem. On the positive side, the conclusion is that the stale rate would be low under the modified tie-breaking rule. However, on the negative side, the results suggests that the best response strategy may depend on the global hash power of the network. This creates a potential advantage for large miners. Why is that so? Because in the classical setting, anyone, even with little knowledge of the network, can join and adapt a very simple strategy. Simply mine as fast as possible. In the quantum setting, again, there's a dilemma. Each miner has to choose how long or how many iterations to apply. The optimal choice depends on the distribution of the hashing power across the network. And it's reasonable to expect that small miners would have less information about this distribution than large miners. And this might introduce a new form of centralization risk. Okay. What about the security of this new tie-breaking rule? Does it introduce new risks, such as timing attacks? How does it affect other scenarios, like selfish mining, infiltration attacks, pool hopping, and many more issues that are currently known in Bitcoin? And specifically, could it allow new 51% attacks that succeed with less than 50% of the hashing power? Another issue is that a key property of mining is that, and proof of work more generally, is that it's progress free. The fact that you worked for T time, say, unsuccessfully doesn't improve or has no effect on your chances of succeeding in the next minute. Quantum mining breaks this property, right? So what are the broader implications of this? So one obvious implication is that if you have a mining machine that is twice as fast, would be worth 4 times as the slower machine. Unlike the classical setting where other things being equal, it would be worth twice. But are there any other ramifications? Lastly, while we understand the downside of a high stale rate in the classical setting, for example, in the context of selfish mining and the longer confirmation time that this implies, the consequences of a high stale rate in the quantum setting are far less understood. So in part 2, we discussed the long-term setting, where all mining is done by quantum miners. In part 3, we'll discuss the mid-term setting, where the first quantum miner will join the network. We'll be concerned whether a small quantum miner with, say, 1% of the hashing power we'll be able to break Bitcoin by using some malicious strategy and outperform all the other classical miners and generate all the new blocks in the chain and, say, perform double spend attacks. Luckily, it was shown by Kojokaro et al. That in a simplified model called the Bitcoin Backbone Protocol, the answer is no. A small quantum miner cannot double spend. Our main result is that a small quantum miner can generate 100% of the blocks and perform double spend. This is outrageous, right? As it seemingly contradicts everything I said in the previous slide. Now, our attack exploits the difficulty adjustment mechanism used in Bitcoin, which I'll remind you shortly. And the simplified model by Kojokaro et al., namely the Bitcoin Backbone Protocol, explicitly ignores these difficulty adjustments, and therefore there is no contradiction between their works and ours. So let's recall Bitcoin's difficulty adjustment mechanism. So in Bitcoin, there is a parameter called the target, denoted T, such that the block is considered valid only if the hash of the block header is smaller than T. Now, in Bitcoin, the goal is to produce a block every 10 minutes on average. But what happens if miners join or leave the network? If the target remains fixed, the block frequency could increase or decrease depending on the total hashing power, which we want to avoid. So to regulate the block production rate, Bitcoin uses a difficulty adjustment mechanism, which is the following. Every 2016 blocks, which should happen every 2 weeks, T is adjusted to stabilize that rate. So, for example, if the last 2016 blocks were produced in just 1 week instead of 2, then blocks are being found too quickly, about once every 5 minutes. So to compensate, the difficulty is doubled by cutting the target in half. Conversely, if blocks are found too slowly, the target is increased. We'll also recall the fork choice rule used in Bitcoin. So, which tip is chosen when there is a long-range fork? Sometimes people refer to Bitcoin's fork choice rule as the longest chain rule, but this isn't entirely accurate. The actual fork choice rule used in Bitcoin is the most work rule. Honest miners follow the chain with the most cumulative proof of work. Suppose the state of the blockchain is as shown as in this concrete example. After this red line, there is a difficulty adjustment, right? Note that the proof of work here continues to be 1, whereas here the difficulty increases by a factor of 2. For whatever, the top chain is clearly longer, right? There are 5 blocks, but the total accumulated proof of work is 5. In contrast, the bottom chain, though shorter, has an accumulated proof of work of 6. Right? The proof of work in these 2 blocks is 2 per block. So each block is in some sense counted twice, and therefore there are 6. The accumulated proof of work here is 6. So according to the most work fork choice rule, honest miners will choose to extend the bottom tip. Now, this distinction turns out to be extremely important for the purpose of this part. We're now ready to provide the intuition for our attack. Suppose that for whatever reason, the difficulty is increased by a factor of 100. Due to the quadratic advantage of Grover's algorithm, it is only square root of 100, that is 10 times harder for a quantum miner to mine one such block. But each such difficult block is counted as 100 easy blocks. So the effective power of the miner increases by a factor of 10 due to this increase. So to conclude, if the difficulty is increased, the hashing power of quantum miner increase relative to the classical miners. So as we will see in the attack, the quantum miner will crank up the difficulty and mine blocks in the increased difficulty where it has a big advantage. Let's walk through the steps of the attack using a concrete example in which the quantum miner controls 10% of the total hashing power, right? So as suggested in the previous slide, the goal of the first step is to increase the difficulty. The attacker mines an entire epoch worth of blocks, that is 2016 block, using fake timestamps, making it appear as though the blocks were mined too quickly. As a result, the difficulty in the next epoch increases by a factor of 100. In step 2, the quantum miner continues mining under the new, much higher difficulty. Now the timestamp between the blocks is also faked, but appear to be 10 minutes apart. After completing a few more epochs, the attacker's chain will have the highest cumulative proof of work, and then the quantum miner will publish their private chain. So why does this work? Recall that originally the attacker had only 10% of the hashing power by mining honestly. But by cranking up the difficulty, the effective boost they effectively boost their relative mining power by a factor of 10, again, because of Grover's advantage. Therefore, from the attacker's perspective, it's as if they control 100% of the effective power under the inflated difficulty. Meanwhile, the rest of the network, which consists 90% of the original hashing power, now contributes less cumulative proof of work, and therefore it will be overtaken by this quantum miner. So in the general case, in the first step, we crank up the difficulty by a factor of 1 over r squared, where r is the honest hashing power of the quantum miner. And step 2 remains essentially the same. We simply mine several epochs in that increased difficulty, with timestamps that look like it happened every 10 minutes. Now, the effective hashing power in step 2 of the quantum miner is equivalent to the original hashing power of the network, whereas the other classical miners have only 1 minus r fraction of the hashing power, so eventually the quantum miner will win. I hope you find the attack simple, interesting, and perhaps even elegant. However, in terms of practicality, I don't believe it would be feasible even in the distant future, at least in its current form, as will be explained in this slide. The best quantum computers available today have an order of 100 qubits, and they are extremely noisy. As a result, they can perform computation lasting only about a millisecond. But even if we assume a future noiseless, ideal quantum computer with many qubits and operating at modern clock speeds, say the fastest classical computer available today, which is 10 gigahertz, our most optimistic analysis shows that running the attack would still take at least 800 years. So impractical. It seems highly unlikely that the attack could be executed in the foreseeable future, and asymptotically the runtime is 1 over r squared, epochs. So note that the fact that they're like each epoch is 2 weeks make this extremely large even for small values of r. Okay. Now, what are the possible routes for making the attack viable in the long term? There are several options. So to increase the quantum clock speed by at least an order of magnitude relative to the fastest classical computers we have today, for example, to 100 gigahertz, I have to say I find this hard to imagine. Maybe target other cryptocurrencies with lower total hash rate or shorter epoch durations. You remember that the epochs, the attack scales like 1 over r squared epoch. So if epoch is, say, a minute, this becomes viable. And another approach is use parallelization. So maybe use many quantum computers. Recall the downside that to reduce the 800 years to just 1 year, you don't need 800 machines. You need 800 squares machines. So about like more than 500,000 quantum machines. Due to the fact that Grover's algorithm doesn't parallelize as efficiently as classical brute force search, as we discussed in part 1. Overall, we present an attack on Bitcoin's proof-of-work mechanism that can be executed by a single quantum miner controlling only a small fraction of the total hashing power. The attack exploits Bitcoin's difficulty adjustment mechanism, and the asymptotic running time of the attack is on the order of E over R squared, where E is the epoch duration, 2 weeks in Bitcoin, and R is the quantum miner's relative hashing power. The attack is unrealistic for a single quantum computer, even in the far future under reasonable assumptions, meaning unless there is a huge surprise. Perhaps it could be made feasible with around 1 million quantum computers. I'll end with a few future directions and related questions. Can the attack presented in part 3 be refined to make it practical? Although there's a major topic I haven't discussed at all, though I'm sure you would find interesting, but it is orthogonal to the focus of this talk. This topic is called quantum money. This is a form of money that shares some properties with physical cash, but with the advantage that it can be transmitted over a quantum communication channel. Think of a quantum internet. And furthermore, its unforgeability is based on the no-cloning theorem, a fundamental principle of quantum mechanics, unlike the cash we use today, which is forgeable. Modern proposals for quantum money can be used to upgrade cryptocurrencies like Bitcoin and address some of their limitations. For example, Bitcoin's scalability problem. For more details, see these two works. Thank you all very much for your time and attention, and I hope you found the talk interesting. Bye-bye.